So here we are with the third part of the A-level day clock reaction work, and this was where you did the same mixtures, right? 0.25 molar of the peroxide, 5 mils of the Ki, 2 mils the H2SO4, 2 mils of the sodium thiosulfate, took it up to volume of 20 milliliters using the appropriate amount of water. But what you did here was you did it at different temperatures. So you each had your own water bath, you popped in the same concentration, so we're keeping those the same now, but we're changing the temperature. Those water baths were set at 25, 30, 35, and 40. And when I did it, these were the data that I got. Now, filling things in here, first of all, temperature in Kelvin is what you must always use anytime you're doing any kind of calculation associated with gas laws, associated with kinetics, etc., generally associated with R, the gas constant. And so using Kelvin, Kelvin is degrees Celsius plus 273. Absolutely no reason to put in the 0.15. I mean, we're lucky to be working to 3 sig figs, let alone 5 sig figs. So pop in 273, add those up, we get 298, 303, 308, and 313. Now, when I did it, what I found were here were the times. So 25 degrees Celsius, these conditions took 70 seconds, increased the temperature to 30, the time went down. In other words, it went faster, as you'd expect, because the rate increases as the temperature increases. Even shorter time at 35, even shorter time at 40. Now we want to calculate the rate of the reaction. Well, this is the same thing that we did in the second part. We mixed things together, mixed the solutions together, nothing happened, nothing happened, nothing happened, and this time is when it suddenly turned blue. It turned blue because we used up all the sodium thiosulfate, and so we can say the rate is the change in thiosulfate, all of it being used up over the change in time, just like we did in the second part. So concentration of thiosulfate was 0.0005. Again, we did that calculation last time, but it's just C1V1 equals C2V2 using 0.005 for C1, 2 for V1, 20 for V2. So take 0.0005 molar and divide it by this time, and we get the rates. And as you can see, they're increasing as we expected. We expected it first of all because the time decreased, but we know also that as the temperature increases, the rate increases. So those are the data for the reaction. Now, if you think back to what you knew about the Arrhenius equation, you know that it relates temperature in Kelvin, blah, 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 not to the rate, but to the rate constant. So the last calculation we need to do is to determine the rate constant. And the way we do that is the way we determine the rate constant at the end of the second movie. We know this is the rate law. Rate equals K times the concentration of peroxide times the concentration of iodide. Here are the concentrations of peroxide and the iodide that we used. So for each of these, we just take the rate. Let's do it for the first one. 7.14 times 10 to the minus 6 equals K times concentration of the H2O2, 0.0125, times the concentration of the iodide, 0.025. Pop that in, rearrange, solve it. K is 0.0228 per molar per second. So we do that for each temperature, and here are the rate constants. So I mentioned the Arrhenius equation a little while ago. Of course, here it is. K, rate constant, is A, the Arrhenius factor, Arrhenius constant, which is a constant for a given reaction, times E to the power of minus EA, the activation energy, constant for a given reaction, over R, constant for everything, times T, a variable. So the Arrhenius equation shows how the rate constant, i.e. the rate, changes with the temperature. Now this is pretty gross looking. So we often rewrite it, natural log of K is natural log of A minus E over R times T. And if I rewrite that ever so slightly, you can see a rather cool thing about not just the Arrhenius equation, but all kinds of yucky equations when you think about it like this. What we now have is we've got a variable, natural log of K, equals a constant, minus another constant, times something to do with another variable, but not T, 1 over T. Now this is a straight line relationship. Variable, constant minus a constant times another variable. If I was to just plot K against T, I would get a yucky looking graph. If I plot log k on the vertical versus 1 over t on the horizontal, well, now I get a straight line. The intercept is the natural log of a, but we don't care about that. The slope of this line, though, is minus ea over r. In other words, the constant multiplied by that x variable. So if you're studying a reaction and you want to determine the activation energy, for example, you do the reaction at different temperatures in which you measure the rate constant. You then plot log of the rate constant against 1 over t, and you get this straight line from which you can effectively read the activation energy. And of course, that is exactly what we did. Different temperatures, different rate constants. We don't want t, we want 1 over t, so that's 1 over t there. We don't want k, we want natural log of k, so that's natural log of k there. Check all these in your calculators to make sure you're good with it. And then I plotted out using my trusty Excel. Along the x-axis, we have 1 over t, so there are 0.003 something or other, 0.003 something or other. Vertical axis, we plotted natural log of k. There was minus 2.9, minus 3.2, etc., etc., etc. Okay, and my nice little calculator told me that the equation for this straight line, and it was a beautiful straight line, look at that, y, right, equals minus 4951.9x plus 12.84. Intercept 12.84, well, that's the natural log of a, don't care about that. However, the slope is minus 4,952, call it, and the slope of this graph is minus the activation energy over r. R is, of course, 8.314, so therefore the activation energy is 4952 times 8.314, which is 41,170 joules, or 41.2 kilojoules per mole. Hope you enjoyed the A-level day. Hope that you got something out of these little video run-throughs. Goodbye.